Okay, this is Dr. Satish Singhal again. Hello, friends, colleagues, students, C# learners, and YouTube crowd. I'm going to show right now the caution in the use of relational or comparison operators when comparing floating point numbers, a C# example. Well, if you saw my examples for doing if and else, you might have noticed already that I pretty much stayed away from using comparison or relational operators when comparing the floating point numbers. You probably saw that I pretty much compared only the integers, and there is a reason for that. Floating point numbers are not exactly representable inside the computer, and there are hazards of comparing them sometime using relational operators. I'm going to show a program on that in Visual Studio shortly and give you some advice on how to actually compare floating point numbers using relational operators. I'm only going to show example of one relational operator, but same applies to all others also. So first I'm going to show you here. I define an int average where I'm adding the 16 integer 16 three times, divide by 3. So it makes sense to think that exactly 16 will be stored inside int average. Okay, so if 16 is indeed stored inside int average, then this comparison operation will be true, and we should get this output here. But if 16 is not exactly stored inside int average, then else block should be executed, and we'll say int average is not equal to 16. Okay, so let's run this program and see what happens. So notice we got the output that int average is exactly equal to 16. So we got the if block output, so that means int average does store exactly 16. So let's keep this result in mind. In fact, I'm going to mark it and post right here under the comments. And then we have, well, 16 is not a floating point number, it's an integer. So let's try a floating point number and do the same operation on that. So we uncomment this one, and I don't want a confusion from this, so I'm going to comment out this one actually. Just want to keep one output at a time. So here we want to see if same behavior is there in floating point number, that here I added the same number 3 times, divide by 3. So I'm expecting storage here is same as one of these numbers, and I'm expecting that okay, floating point number will behave the same way. So I add 1.6 3 times, divide that by 3.0. So if floating point number behave exactly the way the integer did, my floating point average should store 1.6, and if that is true, then this should be true. And okay, so this should say floating point average. Okay, so if this is true, like it was in the case of integer, I should get this output. But if this is false for some reason, I should get this output. So let's see what happens in this case. Well, wow, what happened here? Well, we are getting the output that floating point average is not equal to 1.6. So this is false. This is false. This does not store 1.6. Okay, so we get this else block output that floating point average is not equal to 1.6. Watch here. That, and this will shock the hell out of some of you. Okay, It is a shocking conclusion. And in fact, I had math students who dropped computer science and said they will never do computer science the rest of their life when they saw this. But you don't have to do that. Trust me. Okay, the reason for that is that 1.6 is not exactly representable inside the computer, because there is no way you can build 0.6 fraction by sum of 1 by 2, 1 by 4, 1 by 8, and so on. Only those floating point numbers are represented exactly, which can be built by fractions such as 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. 1.6, 1.1, they can never be built exactly and represented exactly in a binary system. You can get close, but it will never be exact. So that's why this does not store exactly 1.6. Okay, so you can say, okay, Dr. Singhal, so far so good, but what am I supposed to do in this case if I do need to compare floating point numbers? Well, I'm going to show you a technique. When you compare floating point numbers, you should compare them for small differences or tolerances. So this may store a number higher than 1.6 because we know that this is not true. We know this is not true. So it could store a number higher than 1.6 or lower. So what we do, we take this, subtract 1.6 from that, get the absolute value. So it's not negative at all. It's just a positive difference basically. So get the abs of that, and then we compare it with a very small number like this one. You can increase or decrease this number and see how it turns out. But what I'm saying is that if this, what is stored inside this, and 1.6 are within tolerance of this, then for all practical purposes I'm going to consider them to be the same. Engineers work this way. They never have precise dimension on a product. Table you buy which is 10 feet long will never ever in a trillion quadrillion year be exactly 10 feet. It will be a little lower or a little higher. It will never going to be exactly 10 feet. So real life you work with tolerances. So what we are saying here is that if this number and this number, the difference between these two is less than this very small number, I'm going to assume them to be same. Okay, so if this is true, then we'll say floating point range is almost 1.6. It's not exact, but it's almost. Otherwise we'll say floating point average is not almost equal to 1.6. Okay, so let's compile it and run it. And this time we get a good result. It says floating point average is almost 1.6. So what program is telling us that the difference between this and this is quite small, and for all practical purposes we can consider them to be the same. Okay, so that's how you compare floating point number. If difference was larger than this, then they're not equal. Okay, so I've done this for using the comparison operator. That's how you should compare the floating point numbers. Okay, for small differences, for tolerances, and that's how real life and real engineering works. So be careful, never use relational operators directly between floating point numbers. Always compare them for tolerances. Okay, thanks for watching. This is Dr. Satish Singhal, PhD. Oh, by the way, yeah, I can add a little bit more to it. So what I meant to say was that you can never build 1.6 exactly by combining fractions such as 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, etc., And the fractional part of a floating point number has to be, you have to be able to build it by combination of this fraction. We'll never get 1.6. It doesn't matter how far we go. We can get close to it, but it will never be exact. That's why 1.6 is not exactly representable in the computer, but 1.5 is. 1.5 is built of 1 and half. So 1.5 will be exactly representable in the computer, but 1.6 is not. But of course, when you are doing programs, you never know what shape your number will take place. So you cannot rely on equal equal operator to become sure that they are equal. Okay? Thanks. Bye.